Okay, so today we will start, we will continue, okay, and do the tutorial about everything we have done so far. Example, and the question says the following, okay. It says, consider the following system, okay. It says x plus 2y minus z equals to 3, 2x plus y plus w equals to 4, and x minus y plus z plus w equals 1. Okay, question 1 says find the solution set of the system. So find the solution set of the system. Question 2 says identify the particular solution. Identify the particular solution. Okay, and of course, as you can guess, question 3 is going to be about the homogeneous part. So identify the solution set of the associated homogeneous system. The associated homogeneous system. Okay, maybe let me split the board into two this way. Okay, so now let's answer the questions. So we have solution here. Okay, so before we start part 1, instead of using the system or doing the computation on the system, we have learned a better way, which is to do the computation on the augmented matrix. Okay, makes things easier. So the associated augmented matrix. Okay, so associated augmented matrix is, so we have 1, 2, and 1. Let me do it row by row. So we have 1, 2, minus 1 is 0, and then the constant is 3, and the second row we have 2, 1, 0, 1, 4, and the third row we have 1, minus 1, 1, 1, 1. Okay, so now let's answer the first question. We are asked to find the solution set. So question 1 is Finally, the solution set. And what do? Perform Gauss's method on the augmented matrix. Okay, so you have 1, 2, minus 1, 0, 3, you have 2, 1, 0, 1, 4, and 1 minus 1, 1, 1, 1. Okay. So let's do Gauss's method very quickly, right? So we have minus 2 rho 1 plus rho 2 will give us, let me rewrite that loss properly. Okay, it will give us what? So we have 1, the first row is not changing, 2 minus 1 is 0, and 3 there. So the second row we have 0, minus 4 plus 1 is minus 3, and 2 plus 0 is 2, 0 plus 1 is 1, minus 6 plus 4 is minus 2. And for the third row, what do? We do minus rho 1 plus rho 3. So we have 0 there. And we have minus 3. And we have 2, 1, and minus 2. Minus rho 2 plus rho 3. 1, 2, minus 1, 0, 3. So we have 0, minus 3, 2, 1, minus 2. And here we have 0. Okay, and 0 there. And here is also 0, 0, and 0. Okay, so we have finished with the Gauss's method. Okay, so that's the step 1. We have done the Gauss's method, and then what do? We have to do the back substitution, okay, or parameterize. So maybe let me write some notes here so step 1, to be able to find the solution set, we perform Gauss's method, okay, Gauss's method to get the echelon form of the matrix, okay. Step 2, what do? We parameterize. This concept of parameterization is very, very important, not only in this chapter, but in future chapters when we will go into depth in linear systems, I mean vector spaces. You will see how useful is this concept of parameterization. So make sure you understand it, okay? Parameterize with free variables. The free variables. Okay, so row 2. How do you write row 2? Row 2, so recall we have x there, y, z, w. So row 2 is going to be minus 3 y. So in row 1, x is leading. In row 2, yes, y is leading. But okay, before even we start parameterization, can you guess what is the type of solution for this system? We have 3 types: no solution, unique solution, or infinitely many. Here we have infinitely many because we have arrived at echelon form. We have no contradictory equation or row, but we don't have a row where each variable is leading. we have 4 variables in total, but we have only 2 leading variables, and we have Z and W that are leading no rows. So that means we have infinitely many solutions. So yeah, let me step 2 before we do the parameterization. It's very important to be able to detect the type of solution set we have, okay? Solution set type. Okay, so we have for that, before we make our conclusions, we have arrive at echelon form. Echelon form. We have no contradictory, no contradictory equation or rule. Okay, and we have two variables are not leading. Yeah, there are variables that are not leading any rule. Okay, so two variables are not leading. That means all of this means we have finitely many solutions. Okay, it's very good to know the type of solution we have. Step 3. Now we can parameterize. Okay. And we have infinitely many solutions. But if we have a unique solution, we just perform back substitution and we get that unique element, okay? And because we have infinitely many solutions, that's why we are parameterizing. Parameterize with the free variables. And those variables are the Z and W. So row 3, row 2, let's rewrite row 2. Row 2 is minus 3y plus 2z plus w equals to minus 2. So we have minus 3y is going to be equal to minus 2 minus 2z minus w, and y is going to be 2 over 3. So we have 2 over 3 plus 2 over 3 z plus 1 over 3 w. So we wrote the leading variable, which is y, in terms of the free variables, which are z and w. Okay. Now let's rewrite row 1. Okay, row 1 is x plus 2y minus z equals to 3. And that means x is going to be equal to 3 minus 2y plus z. And we know y, so let's substitute its value into this equation. So minus 2 over 3 plus 2 over 3 z. Okay, I have to be careful with my 3's and z's. They kind of look the same. 3 z plus 1 over 3 w, and then we have plus z there, which is 3 plus 4 over 3 plus, that's minus, why am I writing plus? plus minus minus 4 over 3 minus 4 over 3 z minus 2 over 3 w plus z. That means 5 over 3. We have 5 over 3. And we have z there and z there. So that's going to be minus 1 over 3 z and minus 2 over 3 w. Okay. Is yes, I think that's right, isn't it? Yeah, that's right. Okay, so we have our x there. So that's the x. We have parameterized it. So, but we are not done yet. There is a better way to write the solution set, right? Using a vector notation. So, okay. So, yeah. Let's go to next page. As we have said, x was equal to 5 over 3 and minus 1 over 3 z minus 2 over 3 w and y equals to 2 over 3 plus 2 over 3 z plus 1 over 3 w. Yeah, plus 1 over 3 w. So that's x, that's z. Our solution set is x. We have x, y, z, and w, which is equal to, we have x is a 5 over 3 minus 1 over 3 z minus 2 over 3 w. Y is 2 over 3 is 2 over 3 z and 1 over 3 w. Z is just z and w is just w. Okay, so you can rewrite um, this big vector as the sum of 3 vectors. Okay, so what we do, we have a 5, we write all the constants in the same vector, 2 over 3. When it comes to z, here is 0, w has a 0 constant, plus minus 1 over 3, 2 over 3, 1, and then a 0. All multiplied by 0, z, sorry, plus here we have minus 2 over 3, 1 over 3, 0, and 1 w, such that z and w are free. That means they can take any value. Okay, yeah, they are free. So now let me write down the final solution. So we have x, y, z, w, which is equal to, okay, 5 over 3, 2 over 3, 0, 0, plus minus 1 over 3, 2 over 3, 1, 0, z, plus minus 2 over 3, 1 over 3, 0, 1. W, such that z and w are free. Let me take it here. It's just W there, W. So I think we have answered the first question. So this is the solution set. Find the solution set of the system. And the second part is asking us to identify the particular and the homogeneous part of the solution. If you recall from this lemma in the lecture, it says for any homogeneous linear system, there exists vectors, or let's start with is actually the theorem. Okay, the theorem here, we are here. The theorem says any linear system's solution set has the form P, which is the particular solution, plus a combination of some linear combination of some vectors, C1 beta 1 plus C2 beta 2, etc. So based on this theorem, we can identify, because this is the particular solution and this is going to be the homogeneous part of the solution, okay, the part associated with the homogeneous system. Okay, so here we are asked to identify the particular. So this is going to be the particular solution and this is going to be the associated homogeneous. So we have, this is particular solution, this is C. So here we can rewrite it like this. Based on the theorem I have just showed you. So we have beta 1 multiplied by C1. So our constant is Z, plus beta 2, the vector, this vector, and C2. Okay, so question 2 says identify the particular solution. The particular solution is 5 over 3, 2 over 3, 0, 0. Okay. And the last part of the example says to identify the parts. Okay, what's the question again? The solution set of the associated homogeneous system. Okay, the solution set of the associated homogeneous system. Which is, as you can guess, minus 1 over 3 and 2 over 3. 2 over 3, 1, 0, multiplied by Z, plus minus 2 over 3, 1 over 3, and 0, 1, W, such that Z and W are free. That's the part. Okay. Okay. I think we are done for today. Okay. So I will see you in the next video. Thank you.